Okay, so this is what sort of I had laid out as what I had planned to look at in all of these different lectures. First was introduction, then followed by look at variables which are involved in rheology. I mean, there is a small lecture on governing equations, but it's sort of more to just lay down those equations so that any time we do some rheometric analysis, we look at those governing equations and solve and simplify and then make deductions based on the assumptions which are involved in rheometry. So when I consolidate and give the overall notes to you, it will include that also. And then we looked at cone and plate geometry in somewhat more detail to understand how is the flow measurable, and then looked at some experimental issues, artifacts. And then we started with yesterday Maxwell model linear viscoelasticity, and looked at also linear viscoelastic response, mainly of polymeric systems, but also micellar systems, soft gels, and also looked at linear viscoelasticity during gelation. And then in the morning, we also looked at the yield stress and thixotropy and the elastoviscoplastic structural models. So what remains is sort of quite substantial. So I have tried to consolidate it, and for completeness, though we talked about normal stress differences, I thought I'll just quickly define it before we go on, and I'll do that through this simple model of elastic dumbbell. So I'll do that first, and then in the introductory lecture I didn't mention about extensional rheometer, so I'll spend some time on that and then finally go on to the Gisicus model. So I'm planning to do half hour each for each of these to sort of complete the overall set of contents that we had in mind. So let's look at this elastic dumbbell model, which is useful for polymeric solutions, and it also provides microscopic insights and gives us a constitutive model which corresponds to the Oldroyd B model. So therefore, it has a nice complementary feature to what's known through continuum modeling. And so quickly what I'll do is look at the elastic dumbbell as a model, and then look at the normal stress differences, and then response of the upper convected Maxwell model. So because this is the simplest model that shows normal stress differences, and then a small modification to the elastic dumbbell where the elasticity is finitely extensible and nonlinear elastic, while the elastic dumbbell initially includes a Hookean spring which can extend infinitely. And so bead spring chain models are used quite commonly to describe polymeric systems, and we could do an implicit solvent or an explicit solvent. So generally the theory is based on this kind of a depiction where you have polymer molecules being represented as beads and spring, and these beads are subjected to the Brownian force based on the continuum, the solvent which is surrounding. And the elastic dumbbell model is the simplest possible. So the whole macromolecule, which is a coil-like object, is being represented. The end-to-end of this macromolecule is being represented as two beads which are connected through a spring. And two essential mechanisms which this mechanical analog, microscopic mechanical analog captures is the fact that this polymer chain has an entropic elasticity, in the sense that the conformational degrees of freedom are high when the two ends are closer together, but if we apply shear, then the two ends tend to move apart, and therefore the conformational degrees of freedom reduce and the entropy of the chain reduces. and then, so therefore it would like to spring back, where at equilibrium, the end-to-end basically points, the maximum probabilities, they are very close to each other. And so for what would happen for random walk problems, right? So therefore, we denote the elastic dumbbell through a connector vector. So we have basically in some coordinate system, R2, which is the position vector of first beat, R1 position vector of second beat, and therefore the connector vector Q. And so this connector vector Q tells us about the orientation of the molecule, and also it tells us about the stretch of the molecule. And we use the Gaussian chain approximation to get basically a connector force which is linearly proportional to the extent of stretch. And this is the Hookean spring. And so the Hookean dumbbell is the simplest possible model of polymer solution. And so what we really have is basically kinetic theory of these dumbbells in a solvent. And so we have a distribution function for the dumbbell. If you look at it from the point of view of the description of the system, you have basically the positions of the two beats, and then the the velocities or the momentum of the two beats. So to specify the state of the system, you would need all of these, but then the velocity is assumed to be following Maxwellian distribution, and so it's only the configurational space that we are trying to solve. And therefore then the distribution function is a function of R1, R2 and time. But then we recast the problem in terms of psi of Q, RC, which is the center of mass motion. And center of mass motion is basically bulk motion of this bead, and therefore that doesn't really add anything to the overall problem. So we can again take that out. And so the distribution function therefore is only a function of Q. And so what would you do is to write a continuity equation or the Smoluchowski equation for this distribution function. And then this would be then needed to be solved if you have to get the overall distribution function. But instead of that, what we do is we take continuity equation and then multiply by this orientation tensor or conformation tensor. And so if we multiply by this and then do an integration, basically what we end up getting is a governing equation in Q. Right? So the overall governing equation in this average conformation tensor, which is an ensemble average, basically then gives us the governing equation for the elastic dumbbell. So this is the kinetic theory of dilute polymer solutions. There are no interactions between different dumbbells. The only interactions are between two beads, and through that as to bonded interaction, because it's representing a chain which is covalently bonded, and the spring force is basically the extensibility of the chain. And the other consideration in all of this is the interaction with the solvent. And so the overall set of forces are the drag between the beads and the solvent, and then we have a Brownian force, which is fluctuating force between the solvent, and then we have the connector force. So the overall force balance on each and every bead is just these. We are looking at the limit where there is no inertia, and therefore the sum of these three forces basically equal to 0. And so when you write down the summation of these forces, so this is actually the drag, and then this is the Brownian force, which is related to the distribution function, and this is the connector force. Right, so this is basically the force balance written for the first bead and the second bead. And we can then recast them by saying that one equation is written for the center of mass motion, and the other equation which is written for the change in Q. So basically these equations, which are force balances, can be transformed to Q and RC. instead of letting them in terms of position vector of bead 1 and position vector of bead 2, by just addition and subtraction of these equations, we can eventually obtain these two governing equations. And so this is the basically the evolution equation for Q. Yeah.
So, so there is entanglement between
no,
the
no,
chains.
This is dilute system, and
dilute system
yeah.
only.
So that's what. So it incorporates only two features, which is the elasticity of the chain and the solvent polymer interaction. But solvent polymer interaction also by way of the fact that the polymer has a motion which is relative to the solvent motion, and the fact that there is a fluctuating solvent interaction of the polymer solvent. So polymer chains are basically fluctuating. Its conformations keep on changing, and that is incorporated through Brownian fluctuations of the bead. And so this is a very simple model which can only account for dilute polymer systems. And the modifications to get to realistic models of, let's say, polymeric polymers at higher concentration or melts would first of all need bead spring chain. So assemblage of these beads so that you have multiple, so that polymer molecular weight gets represented. In this, there is no dependency of polymer molecular weight because you are representing it just using one single spring. And then secondly, you would need to add different interactions. For example, this is not even doing a self-avoiding walk. There is no excluded volume in this. The two beads can in fact overlap on each other. So things like that would be added on to get better order theories. And so the continuity equation, or the equation for the distribution function, then you can multiply with this QQ and then do the algebraic manipulation to basically get this governing equation for QQ, which is basically like for liquid crystals and variety of other things. It's the same, conformation tensor, or what else is it called? Any other word for this? Conformation tensor is there. Then generally for liquid crystals also you would use for describing the order in the system. Parameter is a scalar, but generally you would have a tensorial tensor order parameter, I guess, right? Yeah. So this is basically representing that. In comparison to the liquid crystal system, here there is a stretch also. So the QQ length can vary. So you can have basically there is going to be a length which is at the equilibrium, right? So this is in the absence of shear, you will have the Brownian beads fluctuating around some average length, and because of the shearing, then this the length will be higher than this equilibrium length of the spring, and that's what we are sort of interested in finding out by doing this. So if you look at it, there is an evolution of the conformation tensor, and if you look at these overall terms, this is actually the convected derivative of QQ. So if you look at the three terms put together, that is nothing but the convected derivative that we have already talked about. So this is again because we are doing the microscopic model and evolving the governing equation. It turns out that you automatically get the convected derivative, and then that's related to the stretching and the connecting force, because this QQ comes from basically a term which is multiplying the connector force and the vector together, connector vector. And so therefore you get this term, and therefore this spring constant H is involved here as to how rigid the spring is. And then this is the Brownian force. And of course, there is a weighting factor of the bead friction also there. So what we will see is this 4h by z is the relaxation time of this particular system. So the relaxation time depends on how rigid or flexible the spring is and what's the dissipative friction being exchanged between the polymer chain and the solvent. So, and then there is a expression for the stress which is related to the solvent contribution and the polymer contribution. And polymer contribution is one due to the connector force and the other is due to the bulk motion. The fact that when a bead moves from one plane to the other hypothetical plane that we talked about as a, what defines a contact force, when a bead itself gets carried over, there is a transfer of momentum between two sides of the material. So therefore, these are the only two contributions. If you have other interactions like electrostatic or any other interactions, they will all have to be added together to give you an overall stress contribution. But in this case, the beads are really not interacting with each other. They are ideal beads. And so if you look at the constitutive equation, so you can combine the stress and the QQ, and you look at the overall governing equation, you can write it as the solvent contribution and the polymer contribution. And the equation for polymer contribution is a Maxwell model. So with the relaxation time, this is the relaxation time, which is Z by 4H. And so if you have a rod-like system, then there is no elasticity in the system, right? Because this is a dilute rod system. So there is going to be a modification to viscosity, but no elasticity in the system. And when you combine both of these, you get what's called an Oldroyd B model, where there are additional terms which is associated with a solvent viscosity. Then this is the polymer contribution, which you could call as eta P. And then there is an additional time constant, which is associated with basically the solvent and polymer relative contributions. Because if you see here, this is a relaxation time and then this is a viscosity. And but here it is the total viscosity, which is solvent viscosity plus polymer viscosity. So therefore, you now have two time scales in the system. And this other time scale is what also leads to that decrease in the micellar solutions, breakage time and G double prime decreasing and all. Some of that is related to this kind of a time scale. But the main relaxation time, which is elastic dumbbell, is a single relaxation model with Z by 4H as the relaxation time. So generally, of late, rather than writing it in terms of stress, the constitutive relation for these dumbbells is written straight away in terms of a conformation tensor. And this conformation tensor is a non-dimensional conformation tensor, where you say the QQ, the ensemble average, divided by what is the length at the equilibrium conditions. And so you can then do a fair bit of algebra to try to replace this QQ with A and find this QQ equilibrium, and you end up with a fairly simple equation for the evolution equation of the conformation. So you have two equations, the equations of evolution for the conformation, and then this conformation is directly related to the stress. And so these two equations together are what are presented as the model instead of this stress strain rate, that kind of a model. Because experimentally you have access to measurement of A, right? You could measure the orientation of the system and therefore try to compare the evolution and differences, spatial differences of orientation, and then compare. So quickly now, in summary, I'll just try to talk about a few modifications, and these are basically Rouse and Zim models, which are extension to N beads. So methodologically, it remains very similar. However, algebraically and theoretically, it becomes complicated because they become coupled equations, and you will have to use approximations to try to arrive at constitutive relations. So therefore, numerical solutions and Brownian dynamics simulation or various other kinds of simulations are what are used generally to solve these, and much less theoretical expressions are available. The Zim model uses hydrodynamic interaction, which basically has the Oseen interaction between two beads. It's a long range interaction where bead disturbing the solvent around it will interact with the other bead. So Zim is with hydrodynamic interaction, while Rouse is without hydrodynamic interaction. The consequence of having N beads and therefore N minus 1 springs is the fact that now there are different n-1 relaxation times in the system. So therefore, you now have a system which has multiple relaxation modes. And so therefore, it becomes closer to describe the overall response of polymeric systems, however, still dilute, because there is still no interchain interaction. So there are intrachain interactions by way of bonded interactions as well as hydrodynamic interactions, but no interchain interaction. So still for melts and other systems, you would need models which are qualitatively very different. But if you look at the description of the linear viscoelasticity of polymer solutions, Zim model does a really good job. So this is some polystyrene in two different solvents, and you can see that the low frequency response is of course viscous, but at higher frequencies you have power law dependence of both G prime and G double prime, both depending on omega to the power 2/3 as predicted by Zim and Zim model, and so it corresponds quite well. So for dilute polymer systems, incorporating stretching, orientation and hydrodynamic interaction is sufficient to capture the overall rheological response. And even in terms of the molecular weight dependence, the parameter which is called the intrinsic viscosity, which is measurement of modification of viscosity by the addition of a solute. So what you do is you measure viscosity as a function of concentration, and then you extrapolate it to infinite dilution. So which is what is called this intrinsic viscosity. So it's saying that what is the modification to the viscosity of solvent when you add very, very small amount of polymer. And it strongly depends on the interaction between solvent and polymer. So experimentally, we know that the dependence on molecular weight is 0.5 to 0.8 are the exponents. And so Rao's model and Zim model sort of span the kind of exponents that are observed. And Zim model coming somewhat closer. But of course not always capturing, because Zim model also there are no interactions between beads in terms of hydrogen bonding or van der Waals or any other set of interactions. Similarly, the relaxation time and the longest relaxation time and its influence on molecular weight, what's observed experimentally is what is predicted by Zim. So therefore, Zim model provides a fairly satisfactory description of the polymer solutions in terms of its description. So since this dumbbell model also predicts a normal stress difference, we can quickly look at the normal stress differences. And as we said that stress tensor for a simple shear flow for any fluid is only going to have the one non-zero shear stress, and then the other three normal stresses as non-zero. And since we are dealing with incompressible fluids, we cannot really determine P in any case, because for all different pressures, the behavior is going to be identical. So what we do is we actually define the normal stress differences. And so within this concept of achieving a simple shear flow, applying a constant strain rate, and then measuring the normal stresses gives us two independent normal stress differences. And so if you look at just trivial this thing, that Maxwell model in simple shear will give that normal stress differences are zero, because this is a linear model and Maxwell model does not really account for any elasticity in a steady simple shear flow. So it incorporates elasticity at small deformations in oscillatory shear or stress relaxation, but as far as steady state elasticity goes, it basically is a perfectly dissipative system, because long time if you give, Maxwell model is nothing but viscous model. And so the upper convected Maxwell model, which includes instead of partial derivative of stress, a convected rate, that ends up having terms which then include the normal stresses also. So you have the earlier terms of the Maxwell model, and then you have, this is the material derivative, and then this is the term which is associated with convected rate. And if you see here, there is a term like this, right, tau yy and then del tau del Vx by del y. So if you recall, this is just a field where Vx is a function of y. So del Vx by del y is indeed the strain rate that was being applied, and tau xx is also non-zero. So therefore, incorporation of convected rate immediately brings in the normal stress differences and their importance in this case. And so if you look at the upper convected Maxwell model in simple shear, so what you see is tau yy and tau zz at steady state are 0. But tau xx at steady state, even though this term goes to 0, you have this non-zero. So it is basically 2 lambda gamma dot yx into tau yx. So this is the overall normal stress which is present in the system. And so the normal stress difference, which we define in terms of the flow direction and the shear direction, is 2 lambda gamma dot yx into tau yx. Or it is also 2 lambda eta gamma dot yx squared, because tau yx we know is just viscosity times gamma dot. And so this is the gamma dot squared dependence that we see for elastic dumbbell or this upper convected Maxwell model. And we define the normal stress differences based on the flow direction, shear direction, and the vorticity direction. And that's just done by convention. So as I mentioned, you have the first normal stress difference as non-zero, second normal stress difference as 0, according to Maxwell model, upper convected Maxwell model. Generally for polymer melts, it is observed that this first normal stress difference is negative of, so I should say maybe the other way, second normal stress difference is 10 times less and negative, while first normal stress difference is generally positive. But there are many classes of materials, and especially dispersions and emulsions, where negative normal stress, first normal stress difference has also been observed. In fact, one of the sort of patents that I came across while looking at personal care products was design of a cream, and how does the cream feel when we spread it on our skin. So they claim that cream will be perceived as good by the customer if it has negative normal stress difference. So while designing, that's a good parameter for you to check. And it's not a very sort of esoteric quantity. Historically, of course, N1 came about because of fiber spinning and film making in polymer melts. The fact that you have to be able to make films and fibers at fairly large rates, right? In an industry, you want to make them as fast as possible. So you're extruding polymer through a very narrow opening and then extruding it, and whether it forms a nice jet or whether it forms a nice film without undulations or any other instabilities was strongly related to the normal stress difference. So just the way our initial analysis of fluid mechanics starts with Reynolds number as a non-dimensional parameter, for polymer engineers, they would form a non-dimensional number with a normal stress difference and then say, okay, if it's below this, then I will get no problems in terms of the polymer processing of these extensional flow situations. And so therefore, that's how historically this came about. So we define these two material functions as N1 and N2, and the one is related to direction of flow, while 2 is direction of shear, and therefore 3 is basically direction of vorticity. So this is the normal convention. And we also define the coefficients, which are scaled with gamma dot squared. So according to upper convected Maxwell model or Oldroyd model or elastic dumbbell model, psi1 is a constant. So just like saying that the most simple model of fluid flow behavior, Newtonian fluid, shows viscosity as constant, here we have a normal stress coefficient which is constant. And for most of viscoelastic materials, psi1 is a function of strain rate itself. And so it therefore varies and not a constant. And so the small modification to the dumbbell in terms of the connector force is the fact that the force goes to infinity when the a connector vector becomes a magnitude q naught. So q naught is basically maximum extensibility of the chain. So therefore, this is finitely extensible nonlinear elastic model where initially the force is varying linearly and then it basically goes to infinity at a value which is associated with Q naught. And so if you include this in the overall theory, then the governing equations become a little more complicated. And so this is the governing equation for conformation tensor. Looks very similar except these two factors which are associated with nonlinear elasticity of the spring. Otherwise, the elastic dumbbell model was just with the Z and Z equilibrium being constant value which can be taken out. And so these become heavily nonlinear in terms of solving also. So this is the nonlinear term which incorporates, log of Z and its derivative and so on. But in terms of description, so this is somewhat recent data and comparison of hydrolyzed polyacrylamide systems in water, and it has combined normal stresses and shear stresses together. So this is a ratio of first normal stress difference to the shear stress, and for 2-3 different systems, and then a master curve is formed as a function of shear rate, Weissenberg number, which is basically dimensionless shear rate. And you can see that Feeney model describes the results rather reasonably. So with that, we will sort of wrap up this discussion of the dumbbell models. Are there any questions? Yeah.
Yeah, so in Zim model and the Rouse model,
Yeah.
so which is dilute. So in Zim model, you said that hydrodynamics is
Interaction
considered.
is included, yeah.
So now hydrodynamics being a long range interaction, so how do you restrict that like there is no intra-chain interaction? So is it like the dilution limit should be the average?
No, so
distance?
this is even intra-chain hydrodynamic interaction, right? Because polymer chain is a very huge object. So the interaction is still intra-chain.
Intra-chain, not interchain.
No. See, that's what is depicted here. It's the, so one part of, see, this bead otherwise would not interact with that beads because it's too away, either through electrostatic or any other interaction or excluded volume. But they do interact with each other because of hydrodynamic interaction.
Okay.
So even for dilute system, you need the hydrodynamic interaction to describe the solution behavior correctly.
Yeah, no, I was wondering that suppose given that this is little long range compared to other interactions, so how it is restricted not to interact with the other chain?
Other chains, No, so if you increase the polymer concentration, eventually you will reach a regime of screening, hydrodynamic screening. Where basically the other interactions are so strong that this hydrodynamic interactions get screened out. So for, let's say even at 30-40% or 10% of polymer volume fraction, you would start seeing influence of interpolymer interactions and other bonded and non-bonded interactions playing a lot bigger role compared to the hydrodynamic interaction. So it's only for the dilute system where hydrodynamic interaction is extremely important.
Okay, thanks.
Okay. So I'll just quickly spend some time on the extensional rheometers because I skipped through that. So just give some remarks which are related to, so other than doing, attempting lubricated squeeze flow, I myself haven't done any extensional rheology. But generally, one of the things that can be said is shear flows are actually reasonably weak flows in the sense that if we look at two material points and how they are getting separated with respect to each other in shear flow, what you would see is the distance between any 2 points will increase linearly with time. So basically the stretching and the distance between these two material points is linearly with time as you are doing a constant strain rate, let's say, experiment. But if you do a constant strain rate stretching experiment where you take, let's say, fluid between two plates and move them apart, to achieve a constant strain rate you will have an exponential separation So if you look at the position of the plate as a function of time, it's moving exponentially in time. And so any 2 points you look, they are getting separated exponentially in time. So therefore, there is a very qualitative difference in terms of how the microscopic entities which are, being subjected to this kind of a flow situation, how do they react to this kind of, deformation. So that's why the extensional flows, that's why are somewhat stronger, so to speak, because they are doing lot more displacement of relative displacement between material particles. And so, unraveling of macromolecules or orienting of rigid rod-like systems, there is far more effect on in the extensional flow. And so, this is how, so generally what you have is a extensional constant rate. So velocity in the z direction is changing with respect to z. So this is like a cuboid of fluid, a hypothetical cuboid of fluid, which is getting stretched, right? So it's shrinking in x and y planes and it's stretching in z direction. And so the z direction velocity is epsilon dot times z. And that's how then we are achieving a constant rate. So this is very similar to what we were doing, where we were shearing at a constant rate with a gamma dot shear rate which is constant. Now we are stretching at a constant rate. And to do that stretching at a constant rate, basically you have an exponential change in z. So that's the exponential stretching that I was talking about. And so rather than representing the relative positions of material particles in terms of strains, quite often we represent them in terms of what are called the stretch ratios. And these stretch ratios are basically initial length, final length. So it's basically rather than delta L by L, it is L final by L initial. So in case of, let's say, rubber elasticity, when we are again doing this stretching experiment, we are stretching to a very large extent. We do 800% strain. So therefore delta is very large. So instead of describing it at 800% strain, we say it is stretch ratio of 8, because it has been stretched at 8 times its original length. And so the stretch ratio are quite commonly described, and they are basically exponentially changing with a constant strain rate. So as epsilon dot is constant with respect to time, the stretch ratio keeps on increasing, because it's a constant strain rate experiment. And so the strain overall is just present any time minus present time multiplied by the strain rate. And this so therefore there is a constant accumulation of stretching in the system. And if you look at the nonlinear measures of strain, then they give you these, it can be written in terms of lambda squared, and depending on which one you use, you get 1 over lambda squared or lambda squared. So because again, whether it's present which is the basis or any other time which is the basis. So this particular strain measure gets you 1 over lambda x squared, and when you have small deformations, then you again get this minus half epsilon and epsilon. So which is what we learn in sort of school books, where we say elasticity is the strain is basically only epsilon. That is because we are using small deformation in case of Hookean elasticity. But for large deformations, you have basically the nonlinear terms involved in terms of how strain is measured. Because if you recall, this was a multiplication of deformation gradient and transpose of deformation gradient, and then subtracting the unit tensor. Because when there is no deformation, this overall finger strain tensor kind of a quantity becomes unity. And so if you do a steady extension on a Newtonian fluid, the overall stress is basically given by these three terms. So you have pressure and then the 2 mu epsilon dot. This is just purely on the basis of the fact that you have 2 mu d. And the d terms will be del Vz by del z, the z term, which is epsilon dot. And so that's what is this 2 mu epsilon dot. So the overall stress tau zz is 2 mu epsilon dot and then the pressure. And while the other ones, of course, because of incompressibility, there will be a Vx in the negative direction and Vy in the negative direction. And so you have these terms. So since we don't, what we do is we use a boundary condition, then there is some atmospheric pressure, which is, let's say, Pa, and we basically remove pressure, and then we write it in terms of some atmospheric pressure. So now if you divide tau xx, then this is basically equal to 3 mu epsilon dot. And this is what we define as extensional viscosity. So the ratio between a strain and this stress is again defined, because we have normal stresses where pressure is undetermined, we again use the difference between the two normal stresses to define viscosity, what's called the elongational viscosity. So elongational viscosity is sigma zz minus sigma xx divided by whatever is the strain rate which is being applied, the stretching rate. And for Newtonian fluids, as we saw, it's just 3 times viscosity, and this is also called the Troughton ratio. So in many of the polymeric systems, not only we will not get 3 times shear viscosity, but many times we will also not reach a steady state, because in all of this, what is being said is when the epsilon dot is constant, right, you will reach a value of stress which is also constant. So there is a steady measurement, just the way we did for shear. But in many polymeric cases, the stress will actually increase and diverge, and then the sample will break. So you never really reach a steady state in actual measurement of the system. So there is a strain hardening of the system, and then there is a break. But many polymeric systems can also show a steady state behavior. And so if you look at this parameter, which is the elongational velocity, which is being measured at constant strain rate, for a Newtonian fluid, it's 3 times viscosity. For a nonlinear viscous fluid, also it's 3 times viscosity. Though the viscosity may be a function of rate, but it's still analogous. If you measure shear viscosity, you have analyzed the extensional response also. For a linear viscoelastic material also, it corresponds to again 3 times the zero shear viscosity that you get at the lower strain rate limit. But for a nonlinear viscoelastic material, it's a completely different function of the strain rate. So for example, the upper convected Maxwell model reduces to, or Oldroyd-B model reduces to Newtonian fluid in shear, but it does not reduce to a constant viscosity in extension. In fact, it gives us a diverging extensional viscosity. So it does show strain hardening behavior. And
can I ask?
Yeah.
Yes. So in all those extension measurement, like it was this incompressibility is considered. So
right.
For a polymeric material, like let's say rubber-like material, is it a good assumption? Or
yes,
like
yes. Rubber is almost perfectly incompressible material.
Okay.
Yeah.
So 0.5.
Poisson's ratio. Yeah.
Okay.
So many of the systems, I guess that soft matter that we worked with, incompressibility is a reasonable assumption. Any other question? Yeah.
No, I didn't get the the use, because we know there are experimental difficulties even if attaining a constant steady state and the sample deformation,
right,
even if the departure of the plate also. But then, what is the use? Why one should go for extension measurement?
Yeah. So as I mentioned, if I have to make good fibers reliably, what I cannot do, see, so let's say the final diameter of the fiber is 5 micron, right? But I cannot extrude through a capillary which is that thin. So what I do is I extrude it out of a capillary which is, let's say, about 200 micron, and then the jet of the polymer I stretch. And that stretching is done through basically rollers. So what I do is I take that strand on a roller and I rotate the roller quite fast so that the strand gets stretched. So I am actually processing the fiber not by pushing it out of the, that's one part of it, but the real processing is happening and the final dimension is being determined based on this stretching flows. And whether I get a fiber with uniform diameter, or there are instabilities, or can I predict what rate should I rotate this, so that I need to know the extensional viscosity, so that I know what roller torques to use, so that I'll get a speed and so on. So therefore, in polymer processing is one example where you would definitely need to know the extensional behavior. And what has been observed in many of the engineering applications is the fact that you can have two polymer melts which show identical shear viscosity. So they are, Newtonian plateau is there, followed by shear thinning, and seems to be completely identical. But you put it in extensional flow, the behavior is remarkably different. And the prominent example of this is basically branched polymer versus linear polymer. So both of them show zero shear viscosity and shear thinning, but branched polymer, because of the way the entanglements are not able to relax in extensional flow, give you a lot better stretching. So you can achieve much faster rates of spinning and get much thinner fibers reliably.
Then the geometries related to the extensional geometry is somehow different from the steady state or shear geometry.
Geometry in the sense?
What kind of geometry are you using in the extension rheometer? It's not similar to the, not exactly same as the shear rheometer.
Yeah, no, so that's another thing, but right now I'm only saying what is the motivation, right? So given that's the motivation, now we have to try to see how do we stretch a strand of fluid. So then it's experimentally more challenging to do such stretching, because one, you need much finer control and over much longer distances. See, rotational rheometry on the other hand is, confined space, while once you start doing the stretching type of experiments, you start getting, control issues, but it has become better. But so maybe since we are discussing this, maybe I'll skip certain slides and just show this slide. So this is some review which came out a few years ago, and this was basically some standard samples. So this happened in 90s, where they said that, look, everybody is measuring extension, we are all saying extension is important, so let's have just one standard sample. And all these different groups using different techniques are measuring extensional viscosity, and data is just all over the place. So this was the conundrum in sort of 1900s and early 2000s. So of course we have resolved it now, because yes, you can do jet, and you can see, right, there's so many different people trying so many different kinds of techniques. These are the sort of groups, and these are the lots of different things that they were all trying to do. So in all of them, what is the control? Are you really having a extensional flow? Is it extensional only in small region and it's not really extensional in other regions? How much does surface tension play a role? So all of those issues were sort of are dominating, and that is still remains the challenge. So polymer literature, as far as the molding operation goes, the high shear rate is still measured using capillary viscometers. So rotational rheometry, we can't really go to very high shear rates. So the high shear rate rheology is done using capillary viscometer as far as molding and pushing through small dies, that phenomenon is concerned. So that measure that they get of viscosity using capillary rheometry seems to serve them well. But the stretching part of it is still not as well understood. Yeah, you want?
So we often hear of this tubeless siphon kind of experiment as a fun experiment.
Right.
Do these have any practical uses?
No, I mean, not that at least I have seen.
Okay.
Yeah.
Because I would think that, being able to kind of, lift something against gravity would be useful, but, using the property of extensional.
Yeah. So it's like an, perpetual motion machine.
Exactly,
kind of Yeah, so, but I have not seen any sort of, including rock climbing, though it's a spectacular sort of thing. Right. And at least I have not seen any, the way historically I have read it in parts that, when some industry, they were doing some mixing, and then the rod was always getting, dirty, and then the people on the shift were being blamed that, you're not doing your job properly, and later on only they realize that it's actually climbing on the rod and spoiling the rod, and therefore it needs to be cleaned or something like that. But I haven't again seen any practical sort of consequence of it. But it's since directly relates to the normal stress differences, the rod climbing effect, so therefore it's a visual effect to sort of as a demonstrative effect. And tubeless siphon, no, I have not seen. But I guess the feature of recoil and elasticity would be represented in other things. Yeah. But yeah, given all these things related to active, yeah, right, we should say that this is an active matter flowing by itself. And activity is driven by elasticity. So this is the, this is generally a representation of the challenge that was, and it's sort of becoming better, but still these rheometers are not still as common. And maybe also in the answering your question, it's still not very clear should we do this rheometry, right, as clearly. I mean, so both from the point of view of fundamental insights, we are not able to quickly get something and say, oh, we have solved something major. Or from an engineering point of view, the data doesn't seem to be immediately applicable. It's still a work in progress.
Instead of going to strain rate control, let's say, we can do, let's say, step strain kind of measurement, stress reduction kind of measurement in extension. Is it possible?
No, see, the question is again related to sensitivity, right? The amount of stress that is involved and how much, whether you can have sensors to measure that kind of strain. And can you...
because the way you measure the normal stress, simply that
right.
is the measurement, and but right now you don't have to worry about the space, that we don't have to separate the sample more.
Yeah, but see, again, maybe there is an issue related to, so there could be two things. One is the fact that, see, many of the features which are related to these practical situations where you have, stretching to 10 times, 100 times, the kind of physical phenomena that the coil has to undergo, right, polymer chain. So that can get represented only if you do sort of a very large deformation. If you do a step strain, if you do a small step strain, then the polymer chain is not really undergoing the deformation that is representative. So the response you will get will still largely be representative of what happens during shear itself.
That might be true for large deformation, I understand.
Yeah, so then the question is, can I do a step change and have a strand still sort of, fluid strand still behave and then can I hold it and measure? I'll have to look at it, but I have not seen whether people have done those kind of experiments. So many of the functions that we discussed earlier are also described in shear free or extensional mode, and I'll skip through this. And this is the strain hardening that I was talking about. This is basically polyethylene, the branched, and this is the linear polyethylene, and this is also polystyrene, which is linear. So you can see that these are experiments at different strain rates. So I don't know whether it's visible, but this is 30 and smaller strain rates 0.003. So this is again an experiment of stress growth. So what we had seen earlier for shear was that you, for a Maxwell model, you basically have an exponential increase in stress. So again, for a Maxwell model, if you look at tau ZZ also, you will see a similar response. So tau ZZ in extension, again there will be an increase in constant value. So linear viscoelastic response would imply an increase in saturation. But for these branched polymers, you have this strain hardening, where the stress with time is basically directly related to strain, because strain rate, which is constant into time, gives you the amount of deformation that's there in the material. So as strain increases, there is a pronounced strain hardening in the material. And what we understand from an engineering point of view is you need a strain hardening material to make good fibers and films. So for example, this polylactic acid, which is a biodegradable polymer, which came about 20 years ago saying, we will replace polyethylene. But then while trying to making films, it all collapsed. And so, but sure enough, the solution was that let's make a branch polylactic acid and add it to polylactic acid, and then it starts, behaving little better, and you can process films to little more clear, control degree. But still, of course, no way as good as polyethylene. And so these are the different techniques that are sort of used for, they depend on the nature of the nominal viscosity that the material has. So lot of these are still related to solutions. A lot of these measurements are based on polymeric solutions, and of course they span in decades of strain rates. And so you have some jetting based methods, the capillary breakup method, as I saw in the morning, that you have your own small capillary breakup device, or you can have the filament stretching, where you are actually stretching the plates at an exponential rate to achieve a constant strain rate in some part of the fluid. But you can see that Caber works for lower viscosity fluids. It may not work well for the higher viscosity systems, while the filament stretching seems to work for higher viscosity systems. But you have to go to lower strain rates, because stretching at very fast rate in a controlled manner and maintaining the jet is not as easy.
But Caber, it is for high strain rate, right?
No, so yeah, it's high strain rate but lower viscosity. Yeah. And so this is what you can see, that you basically increase the separation between the plates, and then because of capillary forces you have thinning of the jet. So you measure the diameter as a function of time, and then you can back calculate the extensional viscosity. And this I already talked about, sort of challenges. And this is the filament stretching rheometer, where you basically change the length, and you can only have so much length, right, in which you do all this. And within that you need sort of center of the jet, which is actually having truly extensional flow. But this has been somewhat, at least a lot more measurements have come out from this filament stretching rheometer, but it's still not commercially as sort of available, as none of the rotational rheometer companies, for example, have said that we will incorporate this, except this is one attachment which works for melt, which is available for Anton Par or TA or any of the instruments, which is a drum based. Basically there are two drums, and this is one drum, and this is another drum, and you basically wrap your film around it and then raise the temperature so that it becomes molten, and then the drum is rotated. So because you have a rotational rheometer, this can be rotated, and because you are rotating it, you stretch. So you can measure torque and then the stretch. So this is one sort of attachment which is available, but I have not seen lots of data based on these kind of measurements. So again, it looks simple and it looks promising that you can do measurements. So let's say we were working with gels, and the sagging of the gel, the fact that it cannot be there as a film. So all of those complications, make the measurements much more challenging. Okay, and I'll stop here, I think. So this is some fancy sort of AI, ML, and fluid mechanics, and then 3D printing and machining to get very complicated shape of the channel, so that you get very precise flow, which gives you completely extensional components using microfluidics. So this is a very recent paper in Journal of Rheology, which says that we have produced optimized uniaxial and biaxial rheometer. But again, need to be seen whether how effective these will be as devices for long-term use by multiple sets of people. Okay, so this is any questions? Just to sort of close the other thing, I had, I think, just one data which was related to P. Yeah. So this is the elongational viscosity as Troughton ratio, which is basically the elongation viscosity divided by shear viscosity, and which is 3 for Newtonian fluids. So you can see that it starts out from 3, but even Oldroyd B model gives you this diverging viscosity. So in shear, it shows viscosity which is constant, but in extension there is a diverging viscosity. So this is both from a real material which shows no sort of reliability. If I do shear characterization well, I cannot predict what's going to happen in extension, and models also similarly show these features. And both FINI-P and Giesecke's, which are popular nonlinear models, show this increase, but then they show a constant beyond a certain strain rate. But this is all, by the way, not with respect to time, it's with respect to strain rate. So there is a strain rate thickening. So what we call shear thickening, there is a strain rate thickening in elongational flows, which is predicted well by many of these simple models. Yeah.
Yeah, so there is no the stiffening in shear flow, right, for this?
Yeah, yeah. So Giesecke's does show shear thinning, and FINI-P also shows shear thinning.
Thinning, yeah.
Oldroyd B does not show shear thinning.
Okay.
So that way, if you look at FINI-P and Giesecke's are closer to many of the polymeric solutions and worm-like micelles or many of the systems where you will see shear thinning in steady shear and shear strain rate thickening in extensional flow.
Extensional flow.
So they can predict both.
But there is no strain rate thickening in shear flow.
Yeah, these models, none of these models. In fact, so you need different models to actually predict shear thickening of systems. And of course, in polymer literature, there is also talk of shear thickening being present and sort of being missed because we are not characterizing it carefully enough. Because some models do show that. If you make some modifications of these bead spring model which are based on the blob picture, they do show, and there are some measurements, isolated measurements, which do show the shear thickening in polymer systems. But it's far less in terms of the prevalence. Okay, so that sort of wraps up the discussion related to the elongational viscosity. And now this in the last remaining 20-25 minutes, I'll quickly go through some features of LAOS. This is based on older work that was done by Ramya, one of my PhD students. Maybe we can just stretch a bit. I am also feeling tired. Just remaining 25 minutes. Huh? In between, yeah. Especially post lunch, I think it's very heavy. Lunch is heavy, then the material is heavy, and we are. The weather also helps to put you down to sleep. If you move less, then you sweat less, feel less heat. Yeah, they will take time, I think. They timed it perfectly to be ready when we are done. Okay. So I'll summarize quickly, many of you who are doing rheology and large amplitude oscillatory shear would be familiar with many of the things that I'll talk about. Basically looking at large amplitude oscillatory shear of three different systems. One is, maybe I think I'll just use this here. One is a supramolecular gel, which is basically based on what's called a low molecular weight gelator. So it's an assembly of these small molecules which leads to a supramolecular gel. And then we have looked at also a polymer which gets cross-linked either due to ionic cross-links or due to chemical cross-links, and also pluronic systems, the micellar micelles which are based on block copolymers. And so in terms of the nonlinear rheology, what we have discussed sort of is the normal stress differences as a key indicator of the elasticity in the system. But of whatever last 15 years or so, there has been a lot of work related to use of large amplitude oscillatory shear to try capturing the nonlinear rheology, especially for large classes of materials which belong to many of these different sort of systems. And these are different measures which are used in terms of trying to quantify the effect. So since we are now applying still a strain which is large, the overall output, which is in terms of stress, is no longer at the same frequency, and so there are nonlinear contributions, and there are various ways in which we could capture this. So one is we could still look at the first harmonic itself, and so continue to look at the response at the frequency, which is the excitation frequency. But alternately, we could also look at the higher harmonics. We could look at just the Fourier harmonics. There are different sort of decompositions, viscous and elastic decompositions, and there is a Chebyshev based decomposition which gives us again higher contributions, E1, E3, V1, V3, corresponding to the elastic contributions and viscous contributions. Or we could just look at the qualitative response during a shear cycle by looking at what are called the Lissajous plots. So looking at stress versus strain or stress versus strain rate plots. And then what has also been done is through these cycles we have now measures which can measure the strain thickening, strain stiffening, or shear thinning, and all those kind of variations that could be measured. And in the last 10, 12 years, there has been also another sort of method which argues that similar to when we look at the Lissajous plot as a whole, you take a look at the whole cycle. But now when you are trying to get some of these measures, what you do is you find slopes at some selected points, and then you try to find some stiffening ratio or thinning ratios and so on. So you're basically, though you have the whole cycle with you, you are just sort of taking point measurements and evolving a measure. So Lissajous plot is one way of looking at, but it's directly stress and strain. So this sequence of physical processes attempts to evaluate modulus and other quantities throughout the cycle. And we then look at it in a Kolkol representation itself, basically real versus imaginary, G double prime versus G prime kind of a representation of the overall cycle, but in the modulus domain rather than looking at in stress and strain domain. And presumably then you can get ideas of dissipation because values of how G double prime varies. You could get ideas of whether it's predominantly elastic or not, and so on. So I'll spend briefly some time related to that. So I'll skip through some of the details related to these earlier measures. So when this was touted, LAOS, though actually it has become a lot more popular, I'm not sure it sort of is as promising as it would have been when this was sort of written that, for polymer processing, extensional rheometry is different and difficult. So let's do LAOS and I can tell you how the polymer will be for extensional flows. That was sort of one promise, because I am deforming the material to a very large extent, 1000% strain. So maybe the measures that I get through LAOS, I don't need to do extensional rheometry. So therefore, there were many of these kind of promises which were sort of and are still sort of worked upon, but we are nowhere near as clear in terms of understanding of LAOS behavior to actually use it that effectively. And I see of late, especially in food rheology, a lot of applications of these LAOS. So whether it's cheese or whether it's chocolate or whipped cream or all food items, dough, there are lots and lots of measurements of LAOS of these systems. And of course, food systems are extremely complex systems. I mean, they have macromolecular, they have emulsions, they have particulate systems and polydispersity. So you name it, and that's present there. So they do show a very rich class of behavior, variety of behavior. So the way I had sort of planned this was, you look at each and every measure and try and asking some questions and see whether for that particular material system, is there any sort of answer. So the first one is a molecule like this, which is a low molecular weight gelator, because if you look at it has interaction points. So there is a pi, so where pi stacking is possible. There is a hydrogen bonding site. So another molecule, same molecule, if it comes, basically these molecules can stack on top of each other and form, what they do is end up forming a chiral helical structure, where each molecule sort of assembles, and then these chiral assemblies get together and form a fibril, and eventually you get a gel. And very small amounts, again 1 weight percent, 0.5 weight percent of this can basically lead from a salt to a gel kind of a application. So if you just look at G and G double prime with strain, can we say something about the different material systems? And so this just shows that you have a gel formation, and even if you shear or something like that, it reforms. And this is what I meant. If I represent the molecule like this, it sort of forms a helical assembly, and then the helices get together in bundle, and then the overall bundle is forming a three-dimensional network, and this is really the supramolecular gel, which encompasses water, 98%, 99% water, and then the network of these supramolecular gels. And if you look at the linear sort of rheology, it shows a gel-like response. Of course, at low frequencies, there is a possibility that there is a decrease and there are viscous modes, but at least in the present setting, you can't really see. And if there is a yielding, one also doesn't know. But when you look at the G prime and G double prime, you see this pronounced, and also maybe there is a hint of two-step. So these are the features that we start analyzing in terms of looking at focusing on only the first harmonic and then looking at these signatures in the material system. And so this came out quite some time ago that looking at G prime and G double prime, you could have 4 different types of responses. So where both of them decrease, one where both of them increase, and then you have the G, this is a lot more common. So many of the soft matter systems that we are familiar with, we will see that G prime decreases, but G double prime goes through a maximum, and quite often, like in the egg box bundles that I showed, our interpretation was that those egg box bundles come apart at some strains, and therefore a lot more dissipation happens, and therefore G double prime goes through a maximum. So depending on the material system, a lot of our hypotheses are related to some increased dissipation in those strain amplitudes. And so these are the sort of family of mathematical models that we have worked with in terms of looking at the modeling of these systems. And you can see that one has to look at sort of different set of models. So one is the Giesecke's model, because as a nonlinear model, it does a good job. As I said, it shows shear thinning. It does so show the overall extensional viscosity correctly, and it can work for worm-like systems and can work for some of the supramolecular systems also. It can work for some of the physically cross-linked polymeric system also. And then on the other hand, we have these elastoviscoplastic kind of models where if you have an yield stress behavior at low strain rates, then this is something we have looked at. Some the pluronic system, for example, had an yield stress under some conditions. So therefore, we could use an elastoviscoplastic model to try to look at the LOS response of that system. Or we also have a network model where there are the relaxation time as well as the contribution to viscous terms get modified based on how many junction points are there, and the junction points basically keep on, there is an evolution equation that you write for junction points. So these are the different classes of models that we sort of use alongside the LAOS measurements to try to see which one of them corresponds to the experimental measurements, and do we have any hypothesis for the mechanisms in the material which matches with these mathematical models. So that has been the exercise. Yeah.
So about using pluronic. So these are in the micellar phase, is it?
Yeah.
Okay.
Yeah.
So at low temperature.
Right. Yeah.
Okay. And they actually show elastoviscoplastic.
Yeah.
Okay. Very dense.
Right. Yeah. Very dense. Yeah.
Yeah. One question.
Yeah.
The G prime, G double prime we got from, let's say, LOS measurement, and that these are the fast harmonics only.
Right, yeah.
And from the linear viscoelastic model also, whatever, that is the similar parameter you are getting in the large strain only.
No, so a linear viscoelastic model by definition will show G prime, G double prime are constant, because by definition that only has, no, see this contribution is presumably reducing because there are other phenomena which are happening, and we are not accounting for those in a linear viscoelastic model.
Okay, that's why I was asking the kind of model you are showing. You are actually capturing the after the G prime drops.
Yes, yeah, precisely. So these are non-linear viscoelastic models. None of these are linear viscoelastic models, so to speak. Yeah. So for the supramolecular gel, given that we had a network of these fibrillar bundles, we chose this network modification kind of a model, and so the network point, and you write a evolution equation for that, and we had to also use 3 different modes, and then we could explain the overall behavior, which is not included here, but you can only see here actually the sort of match. It's reasonable, I mean, with the 3 modes added together. And so the other question is related to, measurement of Fourier harmonics, where again we basically get only the odd harmonics, because stress is sort of related to strain, and if you look at this I omega t representation, given that you are multiplying with the strain itself, so you have the overall behavior multiplied by strain, and therefore you get only the 3rd and 5th harmonics, which are non-zero in case of the LAOS. One of the features that you can identify about the wobble or breaking of the symmetry of the flow is by looking at whether there are second harmonics present or not. And we do have, we had a geometry which was wobbly. So then we did LAOS measurements there, and yes, you can pick up the other harmonics quite clearly. And so higher harmonics, of course, keep on increasing, and this we had investigated using this physically and chemically cross-linked polymer. So I'll skip through some of this. And then what we do is Lissajous plots, where you have for a perfectly linear elastic material, you just have a stress strain proportional to each other, and for a Newtonian fluid, stress and strain rate are proportional to each other, but they end up being circles in the other representations. And so you can look at the Lissajous plots and then get some idea about what the behavior is. And this is for a physically cross-linked system. So PVA and borax is the alcohol group on polyvinyl alcohol gets cross-linked using borax. And qualitatively, of course, they look very different compared to a chemically cross-linked system. where you can see a strain stiffening much more pronounced here. That's because you have permanent cross-link, and then the finite extensibility of chains comes into effect, and you can see a significant strain stiffening effect when you have a chemically cross-linked system. And so we again looked at some combination of Giesecke's model in looking at describing the overall response of these systems. So, and this was the system which was related to the pluronic system, where we were looking at not just the micellar gel itself, but also look at the presence of a polysaccharide, which is hyaluronic acid. And so what we have is micelles of the pluronic, and in addition we have polymer chains, and it's the combination of these two in terms of their small amplitude and large amplitude oscillatory shear response we looked at. So can we use a model that captures basic mechanisms, and can it be used for both linear and nonlinear rheology? And can we also look at the yield stress and the harmonic ratios or strain thickening ratios? Can they be also captured using a model? And so in this case, we use this yielding-like material as I was mentioning. And maybe I think going through this will require some time, so I'll maybe skip through. But we did different measurements, looked at what happens to the overall viscosity and the relaxation time. We did some light scattering measurements also. And we were able to talk about, how is the behavior pre-yield and post-yield in these kind of system. And this is where some of the literature I remember looking at cages and cage breaking phenomena and those kind of things that I had encountered. So I'll summarize these, and then in the remaining 5 minutes I'll talk about that sequence of physical processes. So the work that I have talked about are all from Ramya's work a few years ago. And so this is the idea of this sequence of physical processes where basically slope at each point of Lissajous plots. And so effectively we are calculating sort of d sigma by d gamma and d sigma by d gamma dot by omega, which is basically again, so looking at the loss modulus and storage modulus, but far more continuously during the cycle itself. And this is again the Giesecke's model representation of what happens under LAOS. So at low strains, of course, we know that it largely shows, basically a ellipsoidal term. But when we start increasing the strain, then you go through these points where curvature change is there and there is strain stiffening or those kind of features. Of course, in Giesecke's model, strain stiffening is absent, but you can see concave and convex region in these. And this is the representation which is based on sequence of physical processes. So in some sense, it's a representation like Lissajous plots, but different shapes. And the presumption or the claim is that by looking at this representation, you might get an insight which is otherwise not available in the usual Lissajous plot. And so the way this is done is again by dividing the Cole representation in all these elastic dominant, purely elastic, viscous dominant, and these different regions. So what's called a deltoid, as opposed to the elliptical curves which are the Lissajous curves, the representation in this Cole representation ends up being more like a deltoid. And then the shape of the deltoid and its orientation and its size, and as a function of strain, what happens to this deltoid? Does it go predominantly to more viscous? Does it change its shape? So again, you can look at and might obtain some physical insights which otherwise may have been more difficult to obtain. So it can sometimes complement the Lissajous representation. And so this is the work done by one of my current PhD students, Saveri, where we were looking at again those pectin calcium gels, but at large amplitude oscillatory shear. And you can see a pronounced sort of G double prime overshoot. And so if you look at, I mean, presumably what we are seeing is this unzipping of these egg box bundles. And so how do they get represented? So we are just beginning now to do this analysis on these materials, and at least what you can see is these deltoids actually are shifting as you sort of increase the strain, at least for this system. But if you look at a supramolecular gel that I talked about also, you can see that the shape of the deltoid remains largely similar. So I'm still not, we've still not come around to completely analyzing and, you know, taking deductions out which are not there in when we were looking at Lissajous plots, but this seems like another possibility of analysis for the large amplitude oscillatory shear measurements to be done, and it's sort of becoming more prevalent. I've seen many more papers come out which talk about this depiction. Yeah, yeah.
So how do you decide what the onset of the nonlinear regime is? I don't think this is working.
In the sense, in using the...
Yeah, so you have that shaded area.
Right.
I understand that this is a schematic area, but do you, for instance, you know, look at the elastic stress and look at the deviation from Hookean behavior or something like that?
No, so you're asking this shaded...
Yeah, the left hand, exactly.
This shaded region, yeah. No, so this is only depicting right now. But yeah, so generally we would look at the third harmonic. Also, we would look at, I mean, multiple measures you look at and then sort of decide the linear. You could also plot the stress amplitude versus the strain amplitude and see where the deviation from the linearity. So you do multiple of those and then sort of arrive at a number.
So this starts well before the yielding, right?
Yeah, yeah. Wait, what starts?
No, I'm saying the nonlinearity starts well
probably earlier than what is indicated here.
Perceptible.
Yeah, absolutely, yeah. So looking at just this and saying it's constant and therefore may not be really correct, yeah. It could be much earlier than that. Only worm-like micelle is a perfectly sort of elastic system to very, very large deformations, but otherwise most other systems start showing significant amount of nonlinearity and sometimes not well represented by the first harmonic.
One more. So any of this model, like can they capture this strain stiffening response, this concavity, like which?
Yeah, so that's the claim. So I have not really gone through the literature as carefully.
Okay.
But so this is anyway the representation only for a Gissicus model.
Yeah.
But there are sort of things to say. See, the strain stiffening is a lot clearly visible on a stress strain diagram itself, right? Mm-hmm. So I would not sort of see that maybe that will be even more evident on a plot which is far more complicated. But some of these other claims that we are making in terms of it being more dissipative or it is sort of more energy storing, maybe those deductions may be more easier to see. So that's why it depends on what.
Yeah, but this is based on the model, right? All these.
All these are based on this Gissicus model. Yeah.
But this Gissicus model, this stress strain, although some concavity is there, but experimental measurement it is quite prominent actually.
Right. Yeah, no, that's why Gissicus is a not good model to describe strain stiffening kind of materials.
I was wondering, like, is there a possibility to modify it to take that into account?
So for strain stiffening, you would need So one of the things that we ended up doing was to sort of have, see, this alpha is a nonlinear parameter in Gissicus. So if this is a constant, then you won't see strain stiffening. So the other thing is we combine sort of a weak gel plus Gissicus, then we could get the strain stiffening response. So a weak gel was phenomenologically added, and then you can get sort of a strain stiffening response. Okay. Any other question?
Can I ask?
Yeah, sure.
Regarding the answering to the how you determine the linearity. Is there any ratio kind of thing? Because you told you observe the second harmonic, third harmonic also on the basis of that also. Sometimes you have to take the judgment.
Ratio of?
first harmonic to second harmonic might be.
No, so yeah, there's a guideline. I mean, so generally you would assume that the third harmonic is 0 in linear.
It's very less comparative to your first harmonic.
Yeah. So generally when I see the noisy data, what you would see is even for a linear, you might get 5%, 2% the third harmonic to be of the first, right? So that's within the noise of the system. Only when it gets to 10.1 or higher, then you might start seeing it contributing more.
It's subject to the experiment who is doing this.
Yeah, absolutely, and material
no hard
system.
and fast
right,
rule.
no hard and fast, yeah.
Another point.
You wanted to add? Yeah.
Okay, because the nonlinearity might have different sources.
Right.
Let's say sometime it might be even if bending, fractures, many things can happen.
Right.
And in your model, suppose the alpha parameter where you actually put the nonlinearity.
Right.
How good is it, because the
so that's why so
mechanism.
these models are more phenomenological in nature, right? So in some sense you are capturing it only effectively. So these cannot be related as well to the mechanisms in the system. So if you really need the explanations of these, then you might have to start with some microscopic model and then sort of arrive at a governing equation which models, and still we don't really have as many microscopic models which can show and which can be compared directly with experimental measurements. So some of the simulation results can qualitatively show you that yes, this phenomena is observed, but mapping on to a real experimental system and then doing the comparison is not as sort of as easy. So therefore what we do is we know that from simulations and from theory these are the mechanisms possible. And then we say, okay, in our experimental measurements, we are seeing signatures of those. And when we do a model where alpha incorporates some features of that, and it's also showing the same feature. So it's sort of a roundabout argument to say that we are understanding, reaching closer to an understanding. But in this, we have not directly done the simulations which are directly based on the physical mechanisms.
I have a quick question. Do you have time? Because I know you have to catch a flight.
No, that's fine.
Okay. So this question was about something that you did not get time to touch, which is the strain rate frequency superposition.
Right.
Yeah. So we have used it. It works. But what is the understanding? I mean, why should it work? Given that it is based on the premise that you overlap linear and nonlinear rheological data.
So and it has worked only for some soft gel glassy kind of systems, and I see that over time there has been not as much sort of reporting of work related to that. So I guess regardless of my personal opinion, the general consensus seemed to be that since it worked, let's not consider that it is something very fundamental and therefore start using it. So that seems to be largely the consensus, that it seemed to have worked in some cases, but it seems difficult where large deformation behavior seems to be analogous. So we also did it for one of our systems, and again it seemed to show reasonable agreement. But basis, Until we arrive at, I guess, a good basis to say why does it work, then I think until then it will remain sort of a question mark. Yeah. Okay. Yeah.
Okay, so we have come to the end of this wonderful lecture series, and like to thank Professor Abhijit Deshpande. Thanks a lot for
I thank you all for being here.
Yes. Taking time off from your busy schedule, and also thanks to Subbu and Vani for help with the organization, and Ranjit and Phanindra for help with this computational and setting up these talks and recording. And okay, so I'd like to invite Ranjini, the SCM group coordinator, to present a small memo.
Oh, I see. Thank you very much.
This was really nice.
Yeah.